Pour yourself a glass of water. Right now, if you have one, I'll wait. Now tip it just a little so it spins near the edge of the glass. Watch what happens. You see those little whirls, those tiny spiraling threads of motion? That thing you just made with your wrist, that is one of the most dangerous, unsolved, humbling problems in all of mathematics and physics. We have sent rockets to the moon. We have split the atom. We have mapped the genome of every living thing. We have detected gravitational waves from black holes colliding 1 billion light years away. And we cannot, not fully, not from first principles, explain what just happened in your water glass. I want you to sit with that for a second, because your instinct right now is to say, oh, come on, Feynman, water in a glass, that can't really be hard. And that's exactly the instinct I want to destroy tonight, because science is full of things that look simple and are simple. And then there is turbulence. Turbulence is the wolf in sheep's clothing. It is the thing that pretends to be ordinary and turns out to be the deepest, most terrible, most beautiful problem in classical physics. 400 years of geniuses, Newton, Euler, Navier-Stokes, Reynolds, Kolmogorov, Heisenberg, von Neumann, all of them took a swing. All of them made progress. None of them finished the job. Let me start at the very beginning, which is where I always like to start because beginnings are honest. You have a fluid, water, air, oil, it doesn't matter, and it's flowing. Now, flowing is a word we use all the time and we think we understand it. But what does it actually mean? It means that the fluid has a velocity at every point in space. Every tiny little piece of the water, every infinitesimal parcel is moving with some speed in some direction. And that velocity can be different at every point, and it can change with time. So you have this field of velocities everywhere, shifting and dancing and evolving. The question of fluid dynamics, and the question that has haunted science since before Newton, is this. Given the state of the fluid right now, what will it be doing 1 second from now? 5 seconds? An hour? Can you predict it? For simple flows, yes. When a fluid moves slowly and gently on what we call laminar flow, it behaves beautifully. The layers slide over one another without mixing. If you put a drop of dye into slowly moving water in a pipe, it stays as a streak, a ribbon, perfectly preserved. You can predict every part of it. The math works. Everything is happy. Leonardo da Vinci painted these kinds of flows with those gorgeous spiraling ribbons he sketched in his notebooks around 1510. And he was the first person I know of to look at moving water and ask the hard question. He noticed that not all water flows that way. Sometimes the flow breaks apart into wild spinning eddies. Sometimes it churns and mixes in a way that seems to have no pattern at all. He didn't have the mathematics to describe it, but he had the eyes to see it. And he wrote in his journal, you can still read it, that he found the motion of water so beautiful and yet so terrible in its complexity. Leonardo da Vinci, 1510. He saw the problem and he shrugged wisely. Now let me give you the equations. Don't panic. I'm not going to make you solve them. I just want you to know they exist because the existence of the equations is itself a clue to why this problem is so hard. In 1822 and 1845, two men, Claude Louis Navier in France and George Gabriel Stokes in Ireland, independently derived the fundamental equations of fluid motion, the Navier-Stokes equations. These equations are not mysterious or metaphysical. They are just Newton's second law, force equals mass times acceleration, applied to a tiny parcel of fluid. You account for pressure. You account for viscosity, which is the internal friction of the fluid, the thing that makes honey thick and water thin. You account for how the fluid pushes on itself as it flows, and out come these equations. They look like a dense tangle of symbols, yes, but conceptually they are clean. They say, here is how the velocity of the fluid changes in time, based on the forces acting on it. Here is the nightmare. These equations are nonlinear. That word nonlinear is the most terrifying word in all of physics. It means the behavior of the system is not simply proportional to its inputs. It means that a small change in the initial conditions can produce a wildly, incomprehensibly different outcome downstream. You know this concept colloquially as the butterfly effect. Well, fluid turbulence is the butterfly effect incarnate. It is not a metaphor. It is the actual physical phenomenon that inspired that metaphor. Edward Lorenz in 1963 was trying to simulate weather, which is just turbulent air, on a primitive computer, and he noticed that rounding his initial numbers to 3 decimal places instead of 6 produced weather that looked completely different after a few simulated days. He had rediscovered from the equations of fluid motion something that every river and every storm and every cup of swirling tea has known forever. The future is sensitive to the present in a way that makes prediction beyond a certain horizon effectively impossible. But here's the subtler thing, the thing that separates turbulence from mere chaos, and the thing that has made it so maddeningly resistant to solution. It is not just that turbulent flow is hard to predict. It is that we do not even know, in a rigorous mathematical sense, whether the Navier-Stokes equations always have a solution. Think about what that means. We have the equations. We believe, from every experiment ever done, that these equations correctly describe fluid motion. And yet we cannot prove that there exists a solution at all times. The equations might, under some conditions, develop a singularity, a place where the velocity becomes infinite, where the math blows up, where the physical universe would presumably laugh at us. Or maybe it doesn't, we don't know, and this is not a minor technical lacuna. The Clay Mathematics Institute, an organization that identifies the deepest unsolved problems in mathematics, has listed the Navier-Stokes existence and smoothness problem as one of its 7 Millennium Prize problems. There is $1 million on the table. It has been sitting there since the year 2000. It remains unclaimed. Let me give you a thought experiment that I think captures the essential mystery. Imagine a long straight pipe and you're pumping water through it. You start pumping slowly. The water flows in nice smooth layers and laminar flow. Beautiful, predictable. Now you gradually increase the speed. For a while still laminar. Then at a certain critical speed, and this is the moment I want you to feel, the flow suddenly and violently transitions. The smooth ribbons break apart, whirls form, vortices appear and disappear. The flow becomes turbulent, 3-dimensional, chaotic, and it mixes the fluid so effectively that dye you inject at one point spreads to fill the entire cross-section of the pipe within a pipe diameter or 2. The same fluid, the same pipe, the same Navier-Stokes equations, but a completely different world. The man who first studied this transition carefully was Osborne Reynolds, a British engineer in 1883. He did a beautifully simple experiment, a glass pipe, colored dye, adjustable pump speed, and he watched the transition happen. And he discovered something remarkable. The transition doesn't depend separately on how fast the fluid is going, or how thick the pipe is, or how viscous the fluid is. It depends on a single combination of all those things, a dimensionless number that now bears his name, the Reynolds number. Low Reynolds number, flow is laminar. High Reynolds number, flow is turbulent. This was a profound insight because it said, a mouse swimming in honey is dynamically similar to a whale swimming in water if their Reynolds numbers match. You can study one and learn about the other. The universe has a kind of scale invariance baked into the problem, which is both wonderful and deeply suggestive of some deeper structure we haven't fully unwrapped. Now I want to tell you about Andrei Kolmogorov because his story is one of the greatest episodes of theoretical physics in the 20th century, and almost nobody outside of fluid dynamics knows it. Kolmogorov was a Soviet mathematician, a ferociously brilliant man who contributed to probability theory, logic, topology, and half a dozen other fields. In 1941, in the middle of the Second World War, while Stalingrad was being prepared for siege and the world was collapsing, Kolmogorov sat down and thought about turbulence. He couldn't solve it either. Nobody can solve it in the full sense. But he asked a different question. He asked, even if I can't predict the details of a turbulent flow, maybe I can say something about its statistical structure. Maybe turbulence, despite looking chaotic, has some kind of universal self-similar organization hiding inside it. And here is what he found, and it is beautiful. He imagined that turbulent energy enters a flow at large scales. Think of a big storm or the blades of a propeller or a river bending around a boulder. That large-scale motion breaks down into smaller vortices, which break down into even smaller ones, which break down further still, like a Russian nesting doll, a matryoshka of eddies cascading down to smaller and smaller scales. And at each scale, energy is transferred from larger eddies to smaller ones until the eddies become so tiny that viscosity, fluid friction, can dissipate the energy as heat. This is the energy cascade, and Kolmogorov predicted, with a beautiful dimensional analysis argument, that the energy at each scale should follow a specific power law, the famous 5/3 law. And the energy spectrum of turbulence should go as the wave number to the power of minus 5/3, and experiments confirmed it. Over and over again in pipe flow, in the atmosphere, in the ocean, in the solar wind, 5/3. Kolmogorov's 1941 paper is one of the most cited papers in the history of physics, and what makes it astonishing is that he derived it not by solving the equations, no, not from first principles, but from symmetry arguments and dimensional reasoning. He went around the problem like a master chess player who doesn't attack a stronghold directly but finds the move that makes the stronghold irrelevant. But here is where it gets strange, and I love this part because physics gets honest when it gets strange. Kolmogorov's theory is not quite right. It is spectacularly right in its broad strokes. The 5/3 power law holds beautifully, but in the fine details, the theory has corrections. Experiments show that the turbulent velocity fluctuations are not perfectly self-similar. The statistics of large fluctuations are different from what you'd expect if the cascade were perfectly uniform. The intermittency, the fact that intense turbulent events cluster in space and time rather than being evenly spread, is not captured by the original 1941 theory. Kolmogorov himself revised the theory in 1962, and the revision spawned decades of further work. We now have a zoo of refined theories, none of them fully satisfactory, all of them grappling with this issue of intermittency. Why does energy dissipate in concentrated bursts rather than smoothly? We don't fully know. 400 years in, and there are still layers of the onion we haven't peeled. Let me give you another thought experiment. This one is physical and visceral. You are sitting in an airplane. It is a clear day over the Atlantic. The plane is at cruising altitude, engines humming. And then, you know this feeling, the seatbelt sign comes on and the plane starts to shake. Not the dramatic shaking of a storm, the invisible kind. The plane is bouncing through pockets of air that are turbulent for no visible reason in a perfectly clear sky. This is called clear air turbulence. It happens when two layers of air with different speeds slide past each other, what fluid dynamicists call a shear flow, and the interface between them becomes unstable and breaks into turbulence. It is the Kelvin-Helmholtz instability, named after two great 19th century physicists. You can see it in nature. It's those beautiful wave-like clouds that sometimes form on the edge of a cloud bank, like frozen ocean waves, like Van Gogh's Starry Night. That pattern, those curling billows, is the beginning of the transition to turbulence. Your airplane shake is what comes after those billows finish curling and break apart entirely. Now here is the practical reason this matters, and I want you to understand it is not just academic. Turbulence kills people. It damages aircraft. It is the dominant mechanism of heat transfer in jet engines, where managing turbulence determines efficiency and determines whether the engine burns up. It is the mechanism by which pollutants spread through the atmosphere. It governs how drugs mix in your bloodstream when they are injected. It determines how weather systems evolve, and our inability to fully model turbulence is one of the fundamental limits on weather forecasting. Even with supercomputers that can do 1 trillion calculations per second, we cannot simulate real turbulence directly. Not at the scales that matter. We have to use approximations, models, surrogates. We use what engineers call turbulence models, which are essentially educated guesses about the statistics of the small-scale motions. These models are calibrated by experiments. They are not derived from first principles. Every engineer who designs an airplane wing or a submarine hull or a gas turbine is in some sense working with a theory we know is incomplete. We build beautiful things with it. The planes fly, the turbines spin, the submarines go. but there is a level of truth underneath that we have not yet touched. Werner Heisenberg, yes, the uncertainty principle man, wrote his doctoral thesis on turbulence in 1923. He later said famously that when he met God, he would ask him two questions: why relativity and why turbulence? And he added, with the humor that serious physicists cultivate, that he was fairly confident God would be able to answer the first question. The story may be apocryphal, but it perfectly captures how physicists have felt about this problem for generations. It is not that we are embarrassed by it, it is that we are genuinely awed by it. Turbulence sits at the intersection of mathematics, physics, computation, and experiment, and it has resisted every weapon each of those fields has brought to bear on it. Now, I want to connect all of this to something bigger, because this is not just a story about water and air. This is a story about the nature of complexity itself. Here is what I think is the deepest lesson. We live in a universe governed by simple laws. Newton's laws, Maxwell's equations, the Schrödinger equation, the Navier-Stokes equations. These laws are beautiful and compact. You can write each of them on a napkin. And yet, and this is the astonishing thing, the consequences of those simple laws are unimaginably rich, complex, surprising. The laws of chemistry follow from the laws of quantum mechanics. The laws of biology follow from chemistry. And turbulence is the place where the simple laws of Newtonian mechanics generate a richness that we cannot follow with our mathematics. It is a demonstration, repeated every time water runs over a rock in a stream, that simple rules can produce complexity beyond our current ability to fully compute or predict. Philip Anderson, the condensed matter physicist, wrote a famous essay in 1972 called More is Different. His point was that when you put many things together, genuinely new phenomena emerge that are not present in the individual parts and that cannot be simply deduced from the rules governing the parts alone. You cannot predict turbulence by looking at a single water molecule. You cannot predict it by looking at a pair of molecules or a trillion of them separately. The turbulence is a property of the collective, of the interactions, of the nonlinearity, and it is not reducible in any simple way to the underlying mechanics. This is not mysticism. It is a precise mathematical statement. The equations governing the individual parts do not easily yield the properties of the whole, and turbulence is the canonical, most dramatic, most ancient example of this emergence. This more is different in all of physics. Let me tell you about the number 3, not the philosophical number 3, but a very specific mathematical fact about the dimensionality of space. Turbulence, as I've described it, is a phenomenon that lives in three-dimensional space, and it turns out this is deep. That in two dimensions, fluids behave completely differently. In two-dimensional turbulence, the energy cascade goes the other way. Instead of energy cascading from large scales down to small ones, energy flows from small scales up to large ones. An inverse cascade. Vortices in two-dimensional flow merge and consolidate into larger and larger structures rather than breaking down. This is why the great red spot of Jupiter, which is in a thin atmospheric layer that behaves roughly two-dimensionally, has persisted for hundreds of years. The dynamics of the two-dimensional problem are vastly better understood than the three-dimensional case. Mathematicians have actually proven existence and regularity of solutions to the Navier-Stokes equations in 2 dimensions. The problem is only open in 3 dimensions. 3 is the hard number. The number of dimensions we happen to live in is the one where the equations are most dangerous and most mysterious. You have to appreciate the dark irony of that. I want to talk about computers because some of you are thinking, surely computers have solved this. We have simulation, we have machine learning. Surely we can just run the equations and watch what happens. And the answer is yes and no. Direct numerical simulation, running the actual Navier-Stokes equations without approximation on a computer, works beautifully for small regions at low to moderate Reynolds numbers. The problem is scaling. To directly simulate a turbulent flow at a Reynolds number typical of an aircraft wing, you need to resolve scales ranging from meters down to fractions of a millimeter. The number of computational points required scales roughly as the Reynolds number to the 9/4 power. For a real aircraft, that means you need something like 10 to the 16th grid points. The best supercomputers in the world today have barely scratched 10 to the 12th. We are orders of magnitude away, not almost there, orders of magnitude away. And the Reynolds numbers in geophysical flows, the atmosphere, the ocean, are so much larger that direct simulation at those scales may never be practical within any technology we can currently imagine. Machine learning, you say? Deep neural networks, maybe they can learn the patterns. And people are trying this, and it's fascinating, and there are genuine successes. Neural networks can learn turbulence models that are better calibrated than the handcrafted ones engineers have used for decades. But here is the thing, and this is important, and I want you to feel the distinction. Learning a pattern is not the same as understanding it. If a neural network learns to predict turbulent statistics in a pipe, and it does so correctly, that is useful engineering. But it does not tell you why. It does not give you the mathematical proof. It does not resolve the existence and smoothness problem. It does not tell you whether there is a singularity hiding somewhere in the equations. A very good map of a territory is not the same as a theory of the territory. Science is not satisfied with maps alone. Science wants to understand. That's the whole project. And turbulence, in that deeper sense, is not yet understood. There's a wonderful false trail in this story, and I think it deserves attention because it teaches us something important about how science goes wrong in interesting ways. For a long time in the mid-20th century, many physicists believed that turbulence was essentially a problem of statistical mechanics. The idea was, yes, turbulence is complicated in detail, but statistically it must be like a thermal equilibrium. Just as we don't track individual molecules in a gas, but use statistical mechanics to get temperature and pressure, maybe we could find some analogous statistical description for turbulence. The idea had real mathematical appeal, and it wasn't entirely wrong. Kolmogorov's work, after all, is statistical. But the full analogy with equilibrium statistical mechanics breaks down badly because turbulence is not in equilibrium. It is continuously driven. Energy is being pumped in at large scales, continuously dissipated at small scales, and the flow through that cascade is very far from any thermal equilibrium. The tools of equilibrium statmech just don't apply cleanly, and the decades of work that assumed they would, while not wasted, because something was always learned, also did not crack the fundamental problem. In science, beautiful analogies can lead you to profound truths and can lead you into beautiful dead ends with equal probability. The map is not the territory. The analogy is not the proof. Let me take you somewhere you might not expect. I want to talk about blood, human blood, flowing through arteries. The heart pumps blood in pulses and not in a steady stream. And as blood flows through the aorta, the large artery leaving the heart, it enters a regime of moderately high Reynolds number. And the flow becomes intermittently turbulent. The turbulence is not random noise in this context. It is physiologically important. It helps mix oxygen and nutrients in the bloodstream. It affects shear stress on arterial walls, which affects whether plaques form, which affects whether you get a heart attack. The fluid dynamics of blood in the cardiovascular system is still an active research area in biomedical engineering, and one of the central challenges is modeling the turbulent transition accurately. The equations we use are Navier-Stokes, the same equations Leonardo looked at a water sketch and shrugged about. The same equations that sit on the Clay Institute's list with $1 million bounty. They flow through your aorta right now, and we still do not have a complete theory of them. Here is something else I find deeply moving. The turbulence in the atmosphere and the chaotic, churning circulation of air that makes weather plays a central role in the long-term regulation of Earth's climate. The way heat is transported from the tropics toward the poles, the way moisture evaporates and rises and condenses to form clouds, the way ocean and atmosphere exchange gases, all of it involves turbulence at its core. When we build climate models, the turbulence below the resolution of the model must be parameterized, described by approximate formulae that try to capture its statistical effect without resolving it directly. These parameterizations are tested against observations, tuned, refined, but they carry uncertainty. And that uncertainty is one of the fundamental sources of spread in climate projections. The difference between a climate model that projects 2 degrees of warming and one that projects 3 degrees is not primarily a disagreement about the physics of greenhouse gases. That is well understood. It is largely a disagreement about clouds, and clouds are turbulence. And turbulence is the unsolved problem. So when you hear uncertainty in climate projections, you are hearing, indirectly, the unresolved whisper of the Navier-Stokes equations. I want to address something directly because some of you are starting to feel uneasy. You are thinking if we can't solve turbulence, and turbulence is everywhere, then our science is fragile, our engineering is built on sand. How do planes fly safely if we don't have a complete theory of turbulence? I want to relieve that anxiety, but not by being dishonest about it. The truth is that science operates on multiple levels simultaneously. At the engineering level, we have very good practical models of turbulence. They are imperfect and incomplete, but they are calibrated against enormous amounts of experimental data, and they are safe within the regimes they've been tested in. Planes fly, turbines spin, the Golden Gate Bridge stands. That is real, that is not illusory. The incompleteness of our theory does not make those achievements less solid. Engineering is the art of building reliably on incomplete theoretical foundations, and engineers are very good at it. But at the deepest level of scientific understanding, the level of proof, of mathematical certainty, of derivation from first principles, turbulence remains open. And I think that is not embarrassing. I think it is one of the most honest things science has ever admitted. We are saying, here is the edge of what we know. Here is where human understanding has reached its current limit. Not its final limit, I don't believe in final limits, but its current one. And the edge is not in some exotic corner of physics involving extra dimensions and Planck scale energies. It is in your kitchen sink. It is in the clouds. It is in your blood. That, to me, is magnificent. That is a kind of humility that science earns by being honest about what it doesn't know. Richard von Mises, another towering figure in fluid mechanics, once described turbulence as the last great unsolved problem of classical physics. He said that in the 1940s. And here, more than 80 years later, I am standing in front of you telling you that it's still open. That should not make you despair. I am telling you that the most ordinary thing you see every day, the smoke rising from a candle, the cream spreading in your coffee, the air flowing over your hand when you put it at a car window, is, in a very precise and non-poetic sense, the frontier of human knowledge. The frontier is not somewhere far away, in a laboratory buried under a mountain, in a machine that costs $10 billion. The frontier is in your coffee cup. I want to end with a thought about what it means to have an unsolved problem, because we live in an era that is uncomfortable with not knowing. We want answers. We want summaries. We want the Wikipedia paragraph that tells us what turbulence is in 3 clean sentences. And turbulence refuses. It will not be summarized. It will not be pinned down. Every time we think we have a handle on it, every time a new theory promises to crack it, reality shows us some new subtlety we hadn't anticipated. The intermittency that broke Kolmogorov's original theory, the anomalous scaling exponents that still don't have a clean derivation, the existence problem that has defeated every mathematician who has charged at it. But here is what I believe about unsolved problems. I believe they are gifts, not to the generation that is frustrated by them. No, to the generation that is frustrated, they are a thorn. But in the long view, unsolved problems are where the interesting physics hides. Every time we have cracked one of these deep knots in our understanding, the answer has revealed something genuinely new about the structure of reality, not just an answer to the question that was asked, but a new way of thinking that spilled over into 10 other fields. When Einstein solved the photoelectric effect, he didn't just answer a technical question about light, he unveiled quantum mechanics. When Boltzmann solved the problem of connecting thermodynamics to mechanics, he didn't just solve a physics problem, he invented statistical mechanics. When Noether proved her theorem connecting symmetry to conservation laws, she didn't just answer a mathematical question, she gave us the deepest organizing principle of modern physics. What is waiting inside turbulence? I don't know. But I suspect that when someone, maybe in this room, maybe reading about this room a century from now, finally cracks the full mathematical theory of turbulent flow, the tools they develop will not just explain turbulence, they will change mathematics. They will change the way we think about nonlinear systems, about emergence, about the relationship between the microscopic and the macroscopic. That is how physics works. The deepest problems open the deepest doors. So I want to leave you with this. The next time you are standing at a sink washing your hands and you watch the water tumble and twist and spiral off your fingers in that wild, gorgeous, apparently random way, I want you to know what you're looking at. You are looking at a system governed by a small number of precise equations that were written down over a century and a half ago. You are looking at something that has been measured, photographed, simulated, analyzed, theorized about, and argued over by the best minds our civilization has produced. You are looking at something that has $1 million attached to its name because we cannot yet prove that its equations always make sense. You are looking at the place where Newton's mechanics reaches its limit and says, I have given you the rules. I cannot alone give you the answers. The rest is up to you. And you are looking at it with water that costs less than a penny and is running over hands that are made of the same atoms that were once in that same water somewhere, cycling through oceans and clouds and rivers since before the first cell divided. The equations that govern you and the equations that govern the water you are washing yourself with are the same equations. You are part of the problem. You are made of the unsolved thing. And perhaps, I like this thought even if it's a bit romantic, perhaps that is exactly why understanding it feels like understanding something about ourselves, about what we are made of, about the layer of reality just underneath the layer we can see. We have been at this for 400 years. We will keep going because that is what the problem deserves and that is what we are for.